Hello everybody. In this video we are going to look at the solutions for the magnetism and electromagnetic induction practice test. Let's take a look at the first problem, or the first multiple choice question I should say. It says an electric current generates the magnetic field shown to the right. The direction of the current is, and we have the options of A, into the page, B, out of the page, C, clockwise, or D, counterclockwise. So if the current is going in a clockwise direction, and remember this is a right-hand rule, but because the camera acts as a mirror, I'm going to use my left hand to demonstrate to you. As I curl my fingers around in a clockwise direction, we see my fingers are curling around in the same direction as the arrows. My thumb is pointing into the screen. So the answer for this one is going to be A, into the page. My thumb is the direction of the current. As my fingers are curling around in a clockwise direction, my thumb is pointing into the screen. So that is our first right-hand rule. Question 2. A wire is carrying a current into the page between two magnets as shown below. Which direction is the force on the wire? So let's take a look and see what we have. We have the current going into the page, or in the negative Z direction. So that's my current. My magnetic field, now remember, magnetic field lines always run from north pole of a magnet to a south pole of a magnet. So my magnetic field lines are actually going in the positive X direction or to the right. So if I orient my hand so that my fingers, which is when I use my right hand rule, and again, use my left hand to demonstrate, but my fingers are the current, my palm is the magnetic field, and my thumb is going to be the force. So if I orient my hand so that my fingers are going into the page or in the negative Z direction, my palm is facing to the right, we can see that my thumb is pointing downward. So the correct answer for this problem is going to be B, going down. Problem 3. The magnetic flux through a loop of wire is at a maximum when A, the area of the loop is parallel to the magnetic field lines. B, the area of the loop is at a 45-degree angle to the magnetic field lines. C, the area of the loop is perpendicular to the magnetic field lines. Or D, the area of the loop is at a 180-degree angle to the magnetic field lines. Remember, the magnetic flux is at its maximum when you have the maximum number of magnetic field lines going through the loop. And that's going to occur when the loop is perpendicular to the magnetic field lines. That's when you have the maximum number of magnetic field lines going through the loop, and that's when you have the maximum magnetic flux. So the answer to this problem is going to be C. Problem 4. In the image to the right, a bar magnet is shown with 3 compasses placed around it. Which compasses are pointing in the correct direction? So again, we have a magnet. Our magnet has a north pole and a south pole. We know that magnetic field lines always run from the north pole to the south pole. So my magnetic field lines would be going in this direction on both sides of the magnet. So we can see that, and let me just draw a couple more arrowheads so we can just kind of see what's going on here. So we can see that compass X is pointing in the Y direction, or in the correct direction, I should say. Compass Y is pointing in the correct direction, but compass Z is not pointing in the correct direction. So our answer to this problem is going to be D. X and Y compasses are pointing in the correct direction, but compass Z is not. Problem 5. Electromagnetic induction will cause a current to be observed in a loop of wire near a magnet. A, only when the magnet is moving. B, only when the loop is moving. C, only when both the magnet and the loop are moving. And D, only when there is relative motion between the magnet and the loop. And the correct answer for this one is going to be D. Remember, in order for a current to be induced in a wire by a magnetic field, There only has to be relative motion between the magnet and the loop. The magnet can be stationary and the loop can be moving, or the loop can be stationary and the magnet can be moving. Both of them could also be moving in relation to one another, as long as they're not both moving at the same speed in the same direction, because the relative motion between them would be zero in that case. So as long as there's relative motion between those two, then a magnetic field or a magnet will induce a current in a wire. Question 6. Transformers work when electricity is transmitted as A, AC current, B, DC current, C, AC or DC current, or D, neither AC nor DC current. Transformers work with alternating current or AC current. Transformers don't work well with direct current. Mr. Broderick touched upon that in one of his videos. And remember, that's one of the big reasons why AC current is what we use to transmit our electrical energy from where it is generated to where it is used. The ability to transform or to change the voltage and the current and transport it over long distances is one of the main reasons why Nikola Tesla's AC system beat out Edison's DC system in the early 1900s. And it's what allows us to generate the electricity at a power plant and then transport it sometimes hundreds of miles to its end user. So the answer to this question is going to be A, AC current. Question 7. A current carrying wire experiences a force due to a uniform magnetic field as shown in the diagram. Which direction is the magnetic field? My force is going to the left on the x-axis. My current is going down on the y-axis, or in the negative y direction. So if I orient my hand so that my thumb is facing to the left, and again using my left hand to demonstrate because the camera behaves like a mirror, my fingers are pointing downward, or in the negative y direction. My palm represents the magnetic field. Remember, my thumb is the force, my fingers are the current, my palm is going to be the magnetic field, and I can see that my palm is facing away from the screen or out of the page. So the answer to question 7 is going to be B, out of the page. And remember, this is one of the tips that I gave during one of the many videos that I recorded on this. But we have 3 factors for the second and third right-hand rule. For the second right-hand rule, you have the magnetic field, the force, and the current. For the third right-hand rule, you have the magnetic field, the force, and the velocity, or the direction of travel of the charged particle. Each one of those 3 things needs to be on its own axis. So we can see in this problem that my force is along the x-axis. The current is along the y-axis. So that means automatically I know that my magnetic field has to be on the z-axis. I just need to use my right hand to determine if it is positive or negative. But I can tell right away that my magnetic field has to be on the z-axis. Okay, on to the problems. Problem 8 tells us that a step-down transformer takes an input of 2400 volts of electricity and outputs 120 volts of electricity. If the primary coil has 560 turns, how many turns does the secondary coil have? Let's take a look and see what we're given in the problem. We are given the primary voltage of 2400 volts, the secondary voltage of 120 volts, and the number of turns on the primary coil is 560 turns. And we are being asked to find the number of turns on the secondary coil. So using my transformer formula, I know that the ratio between the secondary voltage and the primary voltage is equal to the ratio of the number of turns on the secondary coil to the number of turns on the primary coil. As we do with all of these, we are going to cross multiply. And when we solve for the number of turns on the secondary coil, I'm going to have NS equals NP times VS over VP. Plug in my known values for that for that equation, and I'm going to have the number of turns on the secondary coil is equal to 28 turns. And again, another tip for these problems, these transformer problems, remember that the voltage and the number of turns are directly proportional to one another. So I can see that the number of turns on the primary, or the voltage on the primary coil is 20 times the voltage on the secondary coil. So I know that the number of turns on the primary coil has to be 20 times the number of turns on the secondary coil. So 560 divided by 20 will give me 28 turns. Problem 9. A 6.50 centimeter wire located in a uniform magnetic field carries a current of 35 amps into the page. If the wire experiences an upward force of 0.85 newtons, find the magnitude and direction of the magnetic field. Let's do the magnitude first, and then we will look at the direction. So our given values in this problem are the length of the wire at 6.50 centimeters. I do have to convert that to meters, so that should be 6.5 times 10 to the minus second meters. It should be 6.50 times 10 to the minus second meters. My current is 35 amps. The force is 0.85 newtons, and we are being asked to find the magnetic field. So if we're looking for the magnetic field, we have the force, the current, and the length. We are going to want to use F equals ILB. Solving that equation for the magnetic field will give me B is equal to F divided by the current times the length. I plug my known values into that equation, and I am going to get a magnetic field of 0.37 Tesla. All right, let's take a look at the direction of the magnetic field. I am told that it carries a current of 35 amps into the page. So it is going in the negative Z direction. So my current is in the negative Z direction, which I represent with the X. I know that the wire experiences an upward force, so my force is going in the upward direction, or in the positive Y direction. So automatically I know that the current is on the Z axis. The force, and let me just write force here, let me just write an F there. The force is on the Y axis, which tells me that the magnetic field has to be on the X axis, because that's the only one I haven't accounted for yet. So my thumb is the force, my fingers are the current, and my palm is the magnetic field. So my fingers want to be going into the page. My thumb wants to be oriented upward. And we see that my palm is facing to the left, or the negative X direction. So the direction of the field is to the left. Problem 10. There is a uniform magnetic field with a magnitude of 1.20 Tesla directed to the right. A 15.5 centimeter wire is moved up the page at a velocity of 17.75 meters per second within the magnetic field. What is the induced EMF in the wire? So I know the magnitude of my magnetic field is 1.20 Tesla. The length of the wire is 15.5 centimeters, which I do need to convert to meters, so that is 15.5 times 10 to the minus second meters. The velocity is 17.75 meters per second. And they are asking us to find the induced EMF in the wire. And here we have the induced EMF represented by the delta V, but I can easily have represented that. Oops, that's a very sloppy Greek letter right there. Let's try that again. You can represent that with the Greek letter epsilon as well. Both of those work for induced EMF. And whichever one you use on the test tomorrow is fine. To find the induced EMF, I know that it is going to equal BLV, or the magnetic field times the length of the wire times the velocity of the wire. I plug my known values into that equation, 1.20 Tesla times 15.5 times 10 to the minus second meters, times 17.75 meters per second, and that is going to give me an induced EMF of 3.30 volts. Problem 11. An electron is traveling to the left at a velocity of 4.5 times 10 to the 6th meters per second. It enters a uniform magnetic field with a magnitude of 3.45 times 10 to the minus third Tesla directed out of the page. What are the magnitude and direction of the force on the electron at the instant it enters the magnetic field? All right, let's take a look again at the magnitude first, and then we will look at direction. I am given the velocity of the electron, 4.5 times 10 to the 6th meters per second. I am given the magnitude of the magnetic field at 3.45 times 10 to the minus third Tesla. This is an electron. So because I know that I'm working with an electron, I know that the charge of the electron is 1.6 times 10 to the minus 19th coulombs. And I'm being asked to find the force. So I know that the force is equal to the charge times the velocity times the magnetic field, F equals QVB. I'm already solved for force, so I don't need to do any rearranging of this formula. I just need to plug in my known values of 1.6 times 10 to the minus 19th coulombs for the charge, 4.5 times 10 to the 6th meters per second for the velocity, and 3.45 times 10 to the minus third Tesla for the magnetic field. When I multiply those together, I'm going to have a force of 2.5 times 10 to the minus 15th newtons. Now let's take a look at the direction. So I know that it tells me that the velocity is to the left. So my velocity, V, is to the left or in the positive X direction. And I know that my magnetic field, B, is out of the page. So I'm trying to draw a circle here. It's not letting me. So that is going to be B out of the page. Sorry, it's not a good circle there. My screen's acting a little funky. So if my velocity is to the left and my magnetic field is out of the page, again, my right hand rule, using my left hand because the camera acts as a mirror, so just for demonstration purposes, I'm using my left hand, but you always use your right hand because it is the right hand rule. I know that my fingers, which are the velocity, want to be pointing toward the left. So my fingers are going to be pointing this way. Try doing it in mirror images. And my magnetic field is going to be pointing out of the page. So my magnetic field, or B, my palm wants to be facing away from the screen. So my fingers are still to the left. My palm now is facing away from the screen. If there was an arrow coming out of my palm, it would be coming out of the screen or away from the screen. And we can see my thumb, which represents the force, is in the downward direction. So the force acting on the electron is downward.